Okay, welcome to the first lecture of computational microelectronics. As you know, my name is Sung Min Hong. So let's get started. The computational microelectronics in Korean is 계산전자공학, and its code number is EC7114, and we have only 3 lecture hours per week. Yes, there is no experiment. And my name is once again Sung Min Hong, and I'm affiliated with School of EECS. So here in this slide, we are now talking about resources already available to you during this semester. 2 years ago, 2018, I made a GitHub repository, and I have uploaded all the materials related to this course already. So therefore, you can directly access to this repository to see the entire semester's lecture materials, and also you can see other guys. So 2 years ago there were also participants, and they gave their homework. So therefore you can check them all. So let me just visit the 2018. So can you see it? Here you can see this is my ID and CM2020F. This is corresponding to this year's repository. However, when you click, then you can see CM 2018F. This is the one for 2 years ago. So this is archive, and you can see it. Oh, here you have lots of things here, and where can you find it? There is a subfolder whose name is 2018, and when you click it, actually you can find many PDF files. So starting from lecture 1, so it was September 3rd, 2 years ago, and when you click it, then you can find, it takes some time, but anyway, you can find the lecture 1, quite similar to the today's lecture material. And let's come back, and you can see that the last one you can find is maybe lecture 23rd, and when we click it, also you can see today's goal is read a NaN list and solve this problem. Yes, so already you have the whole semester available to you. And how about this year? In this year, for example, you can find the CM2020 app, and in this case we have a new subfolder whose name is book, and I will upload the related part of my own book, so therefore you can have a look at it later. And here PPT, so this one will also contain some materials which is used today and all other lectures. So you can see it clearly. And yes, this there are certain folders starting from a capital S, and there is an 8-digit number that is corresponding to your folder. So it means that each of you have to make this folder. So I will show you how can you make these subfolders for your own homework submission. So here you have S20000000. So this is just a dummy one, and when you click it, then you can find files here. Okay, it has only one file, which is just a readme.md file, but later you should submit your homework code and report through this way. Okay, already some guys did it. Yes. So other lecture participants can do the similar thing for performing the homework number 1. Okay, so this is just a brief introduction about our GitHub repository. Of course, I will revisit this GitHub repository once again to show you how can you do this kind of thing, so modification of our main repositories. And you have certain recorded lectures in my YouTube channel. So now it has very simple address, and you can type it, and there you can find a long list of recorded lectures, and there is a playlist devoted to computational microelectronics. So computational microelectronics has two different playlists, which is corresponding to 2018 and 2020. So this is done in Korean. So at the time it was not a regular lecture, that was just a supplementary material, so therefore it was given in Korean. However, in this year 2020, it is a part of our regular lecture, so I will give it in English. So you can make a full advantages of these two different playlists. Let's go to the next slide about the evaluation. First of all, you have to attend this course regularly. So if you miss it, then there will be certain disadvantages to your final score. Here we have 20% weight factors for attendance, and also you know that we have a 1/3 rule in our institute. So if you don't attend your lectures more than 2/3 of entire given lectures, then you will fail. That is one thing. And every week or even every lecture, you have homework. Yes, that takes just half of our entire credit or score. After that, at the end of our class, then our semester, I will give you some theme to you for final presentation. So since we are not allowed to make offline final exam or offline meeting for final presentation, I just decided to receive certain video made by you individually. So please submit your motion pictures to me, then I will watch it and make a certain score on your final presentation. Okay, that will take 30% of our entire score. And if you are coming from Department of Physics or School of Material Science and Engineering, so I wanted to say that there will be no advantage or disadvantage rule. You will be evaluated in equal base. Also, there is no SU participant is allowed. So if you are in this kind of a category, so just switch to letter type participant. Okay, so I guess that this is all about certain materials not related to our actual lecture. So since this is the first lecture, I will just cover very basic and very preliminary contents. Okay, just warming up for our brain. So we start from infinite potential well problem. I guess that all of you already understand this infinite potential well problem. So please give me a feedback about your familiarity about this infinite potential well problem, or have you already solved it before? So if you remember and if you have heard about this infinite potential well, then we can just quickly cover this infinite potential well problem. Infinite potential well problem is simply given by this potential profile. Yes, here we have a certain area where our electrons can move, and here we have other part where our electrons cannot move or cannot access. So simply this forbidden reason can be achieved by this just infinitely high barrier. Since the electron has infinitely high barrier in this part, therefore whatever the energy the electron have, so it cannot penetrate into this barrier layer. So therefore in this case, now we can say that the Schrödinger equation, original Schrödinger equation says that we have a Hamiltonian operator, and when we have wave function psi, then if this wave function is an eigenvector of this Hamiltonian, then we will have a certain eigenvalue E and multiplied by our original eigenvector or wave function psi. So this is the original form, and Hamiltonian operator is given as just sum of kinetic energy operator and potential. So this is still operator, but this is just multiplication. So in this simple problem called infinite potential well, for the reason of larger than 0 and smaller than a, so this part we allow the electronic motion, and electron cannot exist in this part. So boundary condition for these boundary points x equal to 0 and x equal to a, at this point we are now saying that psi should vanish. Also psi should vanish at x equal to a, and in between, in this part, x larger than 0 and x smaller than a, we have just a flat potential whose value is happen to be set to 0. So safely say, we can say the Hamiltonian operator is just a kinetic energy operator. Then kinetic energy operator in this effective mass approximation, we can say this is this one. Yes, this one is corresponding to our kinetic energy operator. Now this form shown in the slide just to say that our kinetic energy times or kinetic energy operator applied on the wave function gives certain eigenenergy E and psi. Okay, so actual calculation or so solution procedure will not be repeated in this material. I have already made it in our L0 material, so please have a look at it. So basically say that all of this problem can be just casted into this form. The important message is now we have a certain second order differential operator. So psi, our wave function, is twice differentiated, and it gives us minus k squared and psi. Since this is squared, so this is a negative number, and since we have negative number, negative eigenvalue for this second order derivative, then we can say maybe cosine function, cosine something or sine something, you know that we have a certain coefficient and coefficient, that can be basis functions for this solution. And all other materials are already covered in lecture 0, so I will just skip it. Our main message in this lecture today is this second order differential operator. This operator itself is at the center of the Schrödinger equation. If we really wanted to solve the Schrödinger equation, then we have to understand the behavior of our second order equation, second order derivation equation. And once again, this is just a one-dimensional structure. One-dimensional structure, only second order differentiation with respect to x-axis, x variable is enough. However, what happens if we have two-dimensional structure and three-dimensional structures? In this case, our second order differentiation operator should be expanded like the y square, and in case of 3D we have to have along x, along y, and finally along g. You know it quite well, and it has, or these operators has its own name. What is the name of these operators? Yes, as you already correctly answer, this operator is called Laplacian operator. So therefore we are interested what is the eigenvalue and eigenvector of Laplacian operator. That is one thing we have to keep in mind. Okay, so although we have more materials, I will just skip because that is already covered in our lecture 0, and just come back only to this diagram. So this is nothing related the actual calculation of infinite potential wave problem, and I just wanted to say why we are considering this infinite potential wave problem. So we are in the computational microelectronics course, therefore everything discussed in this course has certain relationship the real world problem. So then in our infinite potential wave problem, is there any realistic example of infinite potential wave problem? That is my question, and the answer is certainly we have clear resemblance in the real world. For example, let's assume that this length scale, so the region of a well or depth of a well is corresponding to about 5 nanometer and around. For example, 3 nanometer, 4 nanometer, 5 nanometer, or slightly larger, around 5 nanometer. And here we have quite large or high potential barrier which prevent our electron just to stay at this well region. So then where can you find the analogy about this infinite potential well? If we introduce a certain system like silicon, whose thickness is around 5 nanometer and sandwiched by silicon dioxide and silicon dioxide, then that is a good approximation for this infinite potential well problem. Let's say that yes, its thickness is 5 nanometer. this is quite easily achieved in modern technology. And how about the potential barrier between silicon and silicon dioxide? Of course, it's not infinitely high. However, in terms of conduction band barrier, its value is about 3.9 electron volt. 3.9 electron volt is much larger than our thermal velocity. At 300 Kelvin, how large is it? Could you please answer? So at 300 Kelvin, how large is it? So I have to say that just thermal, this is a thermal voltage. So therefore, in order to make an electron volt, then we have to say Q times Vt or kVt. Yes, this is thermal energy, and thermal energy at 300 Kelvin is about, as Mr. An correctly answered, about 20.585 milli electron volt at 300 Kelvin. So therefore, all of you understand in this system, actually this thermal energy is the scale for electron energy. So if the barrier is much larger than this thermal energy, then it can be safely regarded as infinitely high. So you know that, so about 1 electron volt is almost corresponding to 40 thermal energy. So in this case, 3.9 electron volt is roughly say about 160 thermal voltage. So therefore, usually we have exponential function for this energy scale. So exponential minus 160 is involved for some tunneling probability into the silicon dioxide layer from silicon layer. You know, this number is extremely small, so we can safely say in the usual case of ground or near ground state, it can be really easily regarded or safely regarded as infinitely high. Then, natural question is, where can you find a silicon whose thickness is just 5 nanometer and sandwiched by silicon dioxide layer? In reality, of course, we can make it. We can make this kind of system quite easily. But point is, this is really existing at everywhere. For example, if you have a transistor, then every transistor in nowadays or in near future just looks like this. I have to say that not right now, but in a short time, you will have certain kind of devices. This is silicon. And once again, the thickness of silicon is just 5 nanometer. And this is width of our silicon region, and maybe this is somewhat larger, like for example 10 nanometer. This is maybe smallest one, but 30 or 40 or even larger number can be possible. So when we have this kind of shape and covered by insulating layer, yes, then since the length scale along this direction is much larger than the length scale along this direction. Therefore, quantum confinement along this longer direction can be safely neglected. Therefore, in this case, we can say, in the first approximation, we can treat this system as just confined along this direction, and cross-sectional view can be looked as just this one-dimensional infinite potential wave problem. So my answer or my conclusion is the reason why we have to consider this infinite potential well is the transistor's actual shape, actual cross-section is quite easily approximated by this infinite potential well problem. Okay, so then finally let's move to the homework number 1. So homework should be uploaded just on next by next Tuesday, so just before our lecture 2 starts. And how to do that? First, log in your GitHub site. I guess that some of you don't have GitHub ID, and please make it and register, and you can log in. Then your main goal is to make a subfolder, just like I have shown to you. So how about this? So GitHub. Our goal is to make a certain folders like S and your student ID and S your student ID. How can you do that? I will just explain it. So in order to see how to do that, please read my readme file in the example folder. First, you have to fork the main repository. This one is shared by all our students and myself, so you don't have privilege to change it directly. So therefore, by forking this original repository, then you have your own repository. Since that is yours, you can change it. Then please add a new file which is located in the subfolder. So how can you make a subfolder? Actually, in GitHub, there is no way to make an empty subfolder. In order to make a subfolder, you have to make a file inside it. Then the subfolder is automatically generated. So I recommend you to make a readme.md file in your subfolder. The file should contain your student ID and your name. Once you do it, then you have made a local change in your local repository. That is inside your local repository, so therefore I cannot see it. In order to submit your homework, then you have to make a pull request. I think that some of you still this concept is not quite clear. So if you have any questions, please ask me now or send me an email. Then I can try to answer your question. Okay, so do you have any question, especially about homework number 1? If you have a question, please let me know, and please remember that due date. Okay, so thank you for coming for this first lecture. Okay, let's wrap up and see you next Monday. Bye.